So record. Okay, great. And then I will share slides and I will admit 2 stragglers to class. Great. So let's talk about a little semantic security review. There it is. So first, let's do a visual recap of the one-time pad security game, which is also the semantic security game. And so the way the security game works is we have an adversary. Remember, when we're talking about semantic security, this is different than when we are talking about perfect security. And so the key difference between the two is that with semantic security, the adversary is computationally bounded. And we have our challenger. So with the one-time pad security game, the adversary will select 2 messages of their choosing at random from the message space. And close this. And they will send those 2 messages to the challenger. The challenger will then sample a bit 0 or 1 and will sample a K, and they will encrypt either message 0 or message 1 into a ciphertext C. Then they will send that ciphertext C back to the adversary, and the adversary will output a bit, either the bit of either being 0 or 1, their guess as to which message was encrypted by the challenger. So that's the one-time pad security game. I'm going to pause for a second and ask for any questions. I'll give that about 45 seconds. I know I went through that very quickly. So I want to make sure that this is something people requested for review from the previous lecture. So I want to spend some time waiting for that. What's B? So Aruj, are you referring to the B on the challenger side, or are you referring to the B on the adversary side, going out of A? So the B is the adversary's guess of which message was encrypted by the challenger. So the challenger can encrypt either message 0 or message 1. And whether or not it encrypts message 0 or message 1 is dependent on this random sample. Yeah, so M sub B is either M0 or it is M1. I wrote M sub B as a shorthand, just so I didn't have to write an FL statement, right? So I could have written that as if B equals 0, encrypt message 0, and if B equals 1, encrypt message 1. Jared, does M sub B make sense now? Oh, great, okay. And we'll continue. So if you recall from last lecture, we connected semantic security to the message recovery game. Can anyone either in the chat or aloud remind us of what the message of what message recovery is? That's all right. So message recovery is given a ciphertext C. If you can recover the message, you can transform the ciphertext C to the original message M. So with that, we have our adversary B. Now, adversary B is a computationally bounded adversary. We also have adversary A. Now, adversary A is an adversary who can solve the message recovery game. This is a hypothetical adversary that does not exist. But for the purposes of this problem, we're saying if they do exist, if you can beat message recovery, then you can beat semantic security. Therefore, solving the message recovery problem is at least as hard as the problem of solving semantic security. Any questions on that? Okay, I'll keep monitoring the chat, but I'm not seeing any, so I'm going to continue. Yeah, so message recovery is given a ciphertext C, can you recover the original M message M that ciphertext represents? And so what we're doing with this proof is we're saying, if you can recover a message, you can beat semantic security. Therefore, message recovery is at least as hard as semantic security, and vice versa. So we're using the security property of, so what we're doing is we're saying this problem is hard, and by relating this problem to another problem, we're stating that those problems are equivalently hard. So we also have our challenger C. So remember, we're playing the B and C, adversary B and challenger C are playing the semantic security game. So challenger B samples two messages, M0 and M1. Sampling two messages, to remind everyone, is picking two messages sampled uniformly and randomly from the message space. Now, it doesn't actually matter if the adversary samples at uniform random, but it does matter if the challenger does. The adversary then sends those messages, M0 and M1, to the challenger. The challenger, I think my slide got cut off, then samples B0 or B1 and samples K. K, remember, is the key that we're using for, K is the key that we are using to encrypt the messages. Then it encrypts either M0 or M1, depending on which bit is chosen, and it returns C to B. B then sends C to A. Remember, A is the adversary that can beat message recovery. A sends back M prime. That's M with the apostrophe after it. And B says, if M prime equals M1, then you return true or you return 1. And if M prime does not equal M1, then you will return false or 0. So that's how you can use the message recovery game to beat semantic security. Are there any questions on this construction? I understand that the challenger C is cut off on the slide. If we look up at a previous slide, it's the same sampling technique used up here. So we can make that. We can just kind of tie those two together in your head. So I'll wait 45 seconds for any questions on the message recovery game. How does this scale with the number of M's? That's a great question, Jared. So in this case, so I guess I should ask a question. Jared, when you say the number of M's, are you referring to the number of messages the adversary B sends to the challenger C? Or are you referring to the number of times? Yeah, okay. So it actually doesn't matter how many messages adversary B sends to challenger C. If anything, it's actually hard, it actually becomes harder for adversary B to guess if there are more messages. So it's not really to their advantage to pick more than 2 messages. Does that make sense? Or does it? Are you still feeling like we should talk more about the number of messages? Talk a bit more. Okay. So when you have 2 messages, you have a 50-50 chance of guessing whether the message encrypted is message 0 or message 1. If you have 3 messages, you have a 33% chance of guessing correctly whether the message was M0, M1, or M2. By adding more messages, you're not increasing your likelihood of being able to make a correct guess. The problem, the challenge does not get any easier. So if you're an adversary, you want just the smallest advantage you can get. So therefore you want the easiest challenge you can have. Now, you can very easily play the semantic security game by sending up to n messages, right? You could send 100 messages to C, and C will still encrypt just one of them. We're going to talk in this lecture about a different security game that has a slightly different rule regarding that. But for this semantic security game, does that track, Jared? Or okay, it does. Great. Okay, so that was a review of semantic security. I'm going to stop sharing. Then I'm going to open up my slides for our review of stream ciphers. Lectures, stream ciphers, stream cipher. Stream ciphers. Review. Okay. Share screen. Stream ciphers review. Okay. So with that, we're going to move on to our stream cipher review. This down here. Great. So the PRG security game. Can anyone in the chat remind us of what a PRG is? Great. Yeah, great. Pseudo-random generator. And can anyone in the chat elaborate on what a pseudo-random generator is? Thank you for everyone who responded. Take a short input key to generate longer keys. That is great, Audibert. That is what it does. So thank you for refreshing our memory, and we'll keep walking through. So the PRG security game, we have an adversary A. Remember, this is our classic computationally bounded adversary. We also have our challenger C. C will sample a bit, 0 or 1. If B is 0, then it will return a randomly sampled key K. If B is 1, it will return G of S, where S is a secret. Remember that the space of S is smaller than the space of K. And G of S returns a key from the space of K. Then the return value is represented as C, the ciphertext, and then A guesses whether we're in situation 0 or situation 1. So any questions on how this tests whether or not, whether and how this tests the security of a pseudo-random generator? This is definitely a simpler game than the semantic security game. And sometimes simpler games are easier to understand and sometimes they're much harder. So don't feel shy about asking any questions. What's S? So S is the space of secrets. So if you remember from Audiburn's response, the pseudorandom generator G takes a short key of length S. Sorry, takes a short secret of length S. Those secrets, little s, right here, are sampled from the secret space, capital S. Now the secret space is less than the size of the key space. Does that help answer your question, Jared, or are you still feeling unclear? Or there's still some vagaries? Okay, great. All right, so that's going to be our review of stream ciphers. I'm not going to go over the linear transform registers that we talked about because those are kind of ancillary, kind of secondary to the main discussion point. Instead, I was hoping to spend some time talking about our lecture for today, which is block ciphers. So if there are any questions about stream ciphers, feel free to ask while I'm transitioning slides. So Yusuf is asking, can you repeat what G of S was? So the capital G was the pseudo-random generator, and the little s was the secret that was sampled. And so G of S is a generator that takes a short secret and returns a key K. The key K is from the key space, just like our other secret keys we've been dealing with throughout class. Does that help, Yusuf, or should we go through that maybe in a little bit more detail? That helped? Okay, great. So with that, block ciphers. This is really exciting. In today's lecture, we're actually going to cover the first cipher that is actively endorsed by the NSA as secure, and actually the only publicly known cipher that they endorse. So I think it's going to be a really fun lecture. And hopefully after this, you feel even more confident in cryptography. So an overview. So if you remember last lecture in our review, we had just introduced the concept of stream ciphers and used pseudo-random generators to create a basic construction of a stream cipher. We also introduced security games where adversaries and challengers hand inputs back and forth. In this lecture, we're going to build upon those ideas and introduce the block cipher. Block ciphers are often called the workhorse of modern cryptography. They are like super commonly used and are actively used and are battle tested. Okay, so to evaluate block ciphers and why they're useful, we're going to need to have a motivation as to why. So if we play the semantic security game, with a semantic security game, you can send 2 messages at once and you receive back 1 ciphertext. And if you want to replay the game, the challenger is going to resample all of its secrets every time. So effectively, the challenger is creating a new encryption scheme every time you challenge them. So this is limiting, right? In the real world, we can't pass secret keys back and forth every time we send a text. If you think about it, right, you probably by just watching this lecture are streaming potentially gigabytes of data. And with all of that data, if I had to hand you a key to encrypt every 128 bits every single time, that would simply be too inefficient. So we need security schemes that allow us to reuse a key multiple times. This is why we're talking. So this is where chosen plain text attacks are coming up. The idea is we still have our adversary A, and the adversary A over here is computationally bounded. And they can send two messages, M0 and M1. Now, those two messages are sent. I'll highlight them here in red. Those are sent, and then the challenger will pick a bit 0 or 1, and will sample a key, and then it will make and encrypt that message B in ciphertext C and send it back. Now, what I have highlighted in red will be sampled every time this attack runs, right? You can see this little arrow right here says you can run this for as many messages as you want. However, what's highlighted in yellow, sampling the bit at random, or sampling the key K, that only happens once every security game. And the goal is to detect whether we are in scenario 0, where we are encrypting message 0, or scenario 1, where we're encrypting message 1. So are there any questions about the chosen plain text attack or the security game we're playing? This is a new idea, so I'm gonna pause for 60 seconds while we kind of collectively think about, about these ideas. Yes, exactly, Aruj. You can use different M0s and M1s while reusing your key. Great. I'm going to wait a little bit longer for any questions since I know that this is a new concept. All right, well, there'll be plenty of time to ask questions throughout the lecture. So I'm going to clear the screen. And march onward. So to handle this new kind of attack, we need a new kind of cryptographic primitive. Last lecture, we discussed pseudo-random generators. This lecture, we're discussing pseudo-random functions. Pseudo-random functions are functions defined over a key space and a message space, outputting text into ciphertext space. This function has to be efficient. However, this function is not necessarily one-to-one. And this function is not necessarily invertible. Are there any questions on what I mean when I say this function is not necessarily one-to-one or not necessarily invertible? I'll go ahead and pause for about 15 or 20 seconds. Great, we'll keep moving forward. So the second primitive we're going to be using, or really a variation of the first primitive, is a pseudo-random permutation. Now, a pseudo-random permutation is similar to a pseudo-random function. It takes a key and a message and outputs a ciphertext. However, if you'll notice, there's a key difference between the two. And that key difference is this X right here and this X right here. All this signifies is that the message space is the same as the ciphertext space. So there are some pseudo-random functions where the messages might be shorter than the than the ciphertext. However, this is not one of those functions. So we'll continue. These functions also must be efficient. These functions are one-to-one. And there exists an efficient algorithm for inverting these functions. So you can think of these kind of like rectangles and squares. All squares are rectangles, but not all rectangles are squares. All pseudo-random permutations are pseudo-random functions. However, not all pseudo-random functions are pseudo-random permutations. Are there any questions on this concept? I'm going to wait about 30 to 40 seconds to see if any pop up in the chat. Okay, we'll continue forward. All right. So with that, I wanted to talk about the security of these pseudo-random permutations and the pseudo-random functions. A PRF is secure if the function is indistinguishable from a truly random function. Now, a couple of notes on notation here. Something you'll notice about this that you will kind of notice is different than past notations is I have this dot right here. This dot is just think of it as a placeholder input for the given message. The dot is just demonstrating that there's going to be a message going there in the future. And you'll also notice that I'm sampling, the pseudo-random function like this. This is just an easy notation for demonstrating. This is just an easy notation for demonstrating how these functions are constructed. And the random means it's like a random mapping. You can think of it as a similar way of thinking about that. Oops. Cool. Mouse. Clear. All drawings. Okay. A pseudo-random permutation is secure if the permutation is indistinguishable from a truly random permutation. Are there any questions on these security definitions, how we've constructed them, and what they mean? Okay, we're about half an hour into class, so I'm going to go ahead and give us a 5-minute break. So I'll just stop my video and stop the audio, and we're going to return at 6:16. Please take the time to stretch, maybe close your eyes, maybe eat some food. Just a quick break, and then we'll return and discuss how these primitives beat the chosen plaintext attack. Thank you. All right, we're back. So I'll give you 15 seconds for if there are any questions related to pseudo-random permutations or pseudo-random functions. All right, not seeing any. So let's keep going. So again, we're going to play our chosen plain text like TAC game and connect it to pseudo-random functions. So we have our computationally bound adversary A and our challenger C. Our challenger C will sample a bit 0 or 1. If the bit is 0, then they'll sample a pseudo random function. If the bit is 0, they'll sample a truly random function. If the bit is 1, they'll sample a pseudo random function through the encryption function we've defined. Then the adversary will send the message M, and they will receive back a ciphertext 0. Sorry, that should be M0, M1, and they'll receive back C. That's what it's supposed to say. And then they'll output B if they get the game correct. But the general idea here is they can repeatedly call M0 or M1, and the encryption is just the exclusive OR of is the key in the message through the pseudo-random function, resulting in a ciphertext C. Are there any questions on this plain text attack? I got a feeling there might be a couple. I think this slide was less clear than I anticipated, so I'll give that about 30 seconds. While I'm waiting, I'll go through it again. So the challenger samples a bit B. If the bit is 0, it samples a truly random function. If the bit is 1, the encryption function is the key and the message, outputting the message, outputting the ciphertext C, and instead of M0 M1, instead of M0 C0, it should be M0 M1 C0 C1. Oh, sorry. I was misleading everyone. Let's reset this. The point of this game, so please excuse that mistake. I want to re-clarify what I actually meant to say. So the point of this game is for the adversary to guess whether or not the challenger is a pseudo random function or whether the challenger is a PRF. And the PRF is being represented as E, where it takes in K in a message M and returns a C. And the other option is a truly random mapping from M to C. And they can repeat this as many times as they want. Does this make sense? I'm going to wait a minute for questions in the chat or aloud. Yes, so the point of this game is for the adversary A. So let me do some highlighting here. Annotate, draw, highlight. Is for the adversary A to guess whether we're in scenario 0 or scenario 1. Scenario 0 is the truly random function, TR. The scenario 1 is the pseudo-random function being represented as, it's horrible drawing, is the pseudo-random function being represented as this encryption function E. Does that answer the question about what the point of the game is, Stefan? Or does the point of the game still feel slightly unclear? Great. So if an adversary can beat this game with a non-negligible advantage, then they can distinguish between a truly random function and a pseudo-random function. And if you can distinguish between those two, you can break larger security questions. So with that, I'd actually like for this next slide, we're going to do a quick in-class activity. And I'm going to ask everyone to take out their notebooks or pencils or pens or whatever they want to use. And I would like all of you to take a moment and go ahead and draw what you think the security game would be for a pseudo-random permutation. I'm going to give you 3 minutes for this, and then I'm going to ask someone in the class to draw it on the board. Feel free to drop messages in the chat throughout if you have any questions. I might call on you at random to share your drawing. So please feel prepared. And again, you're drawing the security game to determine whether or not an adversary can distinguish between a truly random permutation and a pseudo-random permutation. I'll actually go ahead and type this out. All right, you have about 1.5 minutes remaining. All right, that's been about 3 minutes. I'm going to just pick a random person on the list, and if you feel comfortable, I'd love for you to come off mute and describe your security game for me. So Emily Fang, do you think you'd feel comfortable walking us through your security game that you've drawn? No worries, Emily. I totally understand that. I'm going to pick on another student. Gia, do you feel comfortable sharing your solution aloud? Okay, hearing no response, I'll take that to mean you don't feel comfortable. Um, Edmund, do you feel comfortable sharing your solution? All right, we're feeling shy today. That's totally fine. The good news is I've already come up with my solution, so I can share my solution. So we'll continue onward. So here is the security game. As always, we start with our adversary A. This adversary is computationally bounded. And we have our challenger C. The challenger C samples a bit 0 or 1. If it's 0, they pick the pseudo-random permutation X map into X. So they pick the truly random permutation X map into X. If it's 1, they sample k lowercase k from the key space. Let me highlight something. This is a syntax error. This should read capital K, not line. And they will sample a permutation function. So let me just make that E a P. Okay, well, instead of an E, that should be a capital P. Sorry about that. And then the adversary sends a message X sub 0, and they get back C sub 0. And their goal is to distinguish, and they can do this as many times as they want. And their goal is to distinguish whether or not the challenger is a truly random permutation or a pseudo-random permutation. Again, I'm sorry for the slight syntax error there and using E instead of P. I'll take the slides after lecture. And it gets a bit 0 or 1. So any questions on the security game? Since folks weren't feeling comfortable sharing theirs, I'm guessing there might be a couple of questions. So I'm going to go ahead and put, yeah, go over the diagram one more time. So I'm going to highlight steps that are, the steps that I'm highlighting in yellow are going to be steps that happen only once. So the challenger decides which game they're playing by sampling a bit 0 or 1. The steps I'm highlighting from now on will be in the light green. They're steps that happen every single cycle. So the adversary will send a message X sub 0 from the space X. If you remember from our earlier slide, the pseudo random permutation is the mapping of all messages to ciphertext such that the ciphertext space and the message space are the same space. So let's talk about what that means. That means M, the message space, is 0 or 1 bits, and there's 128 of them. And the ciphertext space is 0 to 1 bits with 128 of them. All I'm saying is that x equals 0, 1 to the 128. And saying m equals c equals x. That's all that this x notation is indicating. So if we continue, depending on which case you're in, you either sample a truly random permutation, or this is equivalent down here to the, I'll highlight that in text. This is the pseudo random permutation, the PRP, and this is the truly random permutation. And so throughout the game, you guess whether someone is in a truly random permutation. You guess whether the challenger chose bit 0 or bit 1, and that's the output bit. And since the output bit happens once, we'll highlight that in yellow as well. Yusuf, do you feel more comfortable with the game now? Or are there parts of the game that you want to talk a little bit more in more detail about? Okay, the X was confusing. That's great feedback. I should have made that a little clearer. Sure. So that equals capital K. Nothing profound there other than when I was making my slides, I must have double tapped instead of single tapping. Does that make sense, Jason? That's just human error. Yep. Thank you so much. Yeah, sorry about that, everyone. I didn't have the time to proofread my slides today. So that's just a small mistake, consequence of that. All right, are there any other questions about the mechanism that I laid out here? So X is everything in blue. So James, when you mean everything in blue, are you talking about, let me just pick a different color. Is what I've outlined in red what you mean by everything in blue? Yeah. So X is just this. In fact, let me just draw an example message. So this is a message. So if X is in big X, then it's 0, 1, and the length of X is 128. Is that helpful, James? Does that help clarify what X is? I'm seeing a yeah, and I'm not sure if it's referring to previous stuff or the current explanation. Okay, I'll go with it's applying to this stuff. Great. So I'm going to wait another 30 seconds actually for just a few more questions about this. I know this proof is a little complicated and the notation wasn't perfect. So I'm just going to give everyone another couple seconds. Okay. Well, this is not your last time to ask questions as always. So I'm going to go ahead and clear the board, take any screenshots you want to take. Okay, I'm going to clear the board and we'll continue onward. So a security lemma. By lemma, I just mean an offshoot. That's not a typo, it's kind of a math term. Security lemma is just kind of a corollary or something that follows, and that's a secure PRP is equivalent to a secure PRF. So block ciphers. Block ciphers can be thought of as PRPs. They are deterministic ciphers. They have an encryption and a decryption function. Its message space and ciphertext are the same, and it shares the Shannon correctness requirement. And just to kind of help clear up any confusion, oh, Edmund dropped out. Just to help clear up any confusion, I'm going to go ahead and annotate, and just going to indicate right here that this equals X from the previous proofs. Any questions on what a block cipher is? We're going to see a couple of real examples in a moment. All right, not seeing any questions. We'll continue forward. Forward. Okay, so let's talk about the history of the electronic code book, or ECB encryption. So this was developed by IBM in the 1970s and became, or in the 1900s, as we're saying nowadays, and it became an official federal information processing standard in 1977. This means it can be used to encrypt. This means it can be used to encrypt classified information. It was released with 4 other ciphers, all of which were more secure, but none of which were totally secure on their own. And, you know, the name electronic codebook derives from the little codebooks used during the Civil War. So that kind of gives you a hint at the sophistication behind this algorithm. So with that, I'm going to go into the mechanism behind this algorithm, behind this implementation of a block cipher. So as you can see, we've got a little machine here. P0 represents the first plain text block. You can think of a string as a bunch of blocks, for example. So let me go ahead and draw on the slide. Hey, let's say we had a message. Let's say our string is hello world, I come in peace. Well, you can break that into the blocks. Hello world, I come in peace. The catch is that blocks are a consistent size. So since these are variable length, they're not really blocks, but I hope this captures the idea of blocks. So mouse. And the way the cipher worked is every single block of the message was encrypted with the same key. And this encryption function was not too sophisticated. In fact, something we've all seen before. It was the exclusive OR. So just annotate that, put that over there. And so every message is encrypted in this manner, and out comes the ciphertext. Now, can anyone in the chat think of any security weaknesses in this algorithm? I'm going to give you 1 minute, and then I'm going to ask some people to share their messages in the chat about the security weakness that they see. Okay, or we're just saying it might take a long time to encrypt. That's definitely true. Yeah, Jared, you're catching on to the situation there. You can basically use the same weakness in the one-time pad, right? This is essentially, this is nothing more than a series of one-time pads being reused, um, which is obviously weak. So thank you for your answers in the chat, but you all nailed it. That's the weakness, is you can use one, this is slow, it takes a long time, but more importantly, it's not secure. So it's deterministic and 1-to-1. Therefore, if M1 equals M2, that follows that C1 equals C2. So you can literally see the output. Like even if you don't want to break the one, even if you use something other, even if the encryption does not equal inclusive OR, which in many implementations it did not, even if you accept this condition, these are deterministic functions. This is supposed to be a PRP, so it just kind of falls apart under any scrutiny. So if it is exclusive OR, the weakness is you can use exclusive OR to break security. If it is if encoder equals a PRP, well, we know that PRPs are both deterministic and 1-to-1. So we basically can guarantee that if P0 and P1 are the same, well then C0 equals C1. And that might not make sense as a security vulnerability now, but I think you're going to find this next drawing enlightening as to why that's a problem. And we're going to describe an attack to break CPA given ECB in a future homework. So this is something the NSA drew up. This is image encryption using ECB. And you can see all it does is it just, permuted all the colors. So you can still see the image. It's not actually that secure. So with that, let's talk about cipher blockchaining. Not quite cryptocurrencies, but I think still an interesting application of cryptography. The way it works is you have a message and an IV. This is like a not, it's kind of a salt, a random string. And you have your key K. Stenography. Oh, yeah. So the message is encrypted. So the message is exclusive ORed with the IV, and then all of that goes in to be encrypted with K, and the encryption function to output the ciphertext C1. And that continues. And the trick is that these are chained together, where this output C1 is used to be exclusive ORed with the next message. So as you can see, by chaining these together, you achieve much greater security. Are there any questions about this and about what it means and how it's made, and maybe questions about its security? I'm gonna hold on for a minute and in the chat. So Marglen, great question. IV. So you can think of IV as a random, a random nonce. So nonce, salt, random, short, key. Different from main key. It's kind of just a bit of, it's kind of like just inserting a bit of randomness into it. And the ciphertext, so when you submit this for decryption, so this is the encryption. If you wanted to decrypt it, the final ciphertext you receive is IV, comma, C1, C2. Like you're given the IV on output. So that way, if you have the key, you can, reverse this. Are there any questions? Because on a future homework assignment, I'm going to ask you to use these again. So I'm going to ask you to write the decryption function. I'll give that another 30, 45 seconds, given that you have a future homework assignment related to this. Can I explain the arrow that leads to the next salt from E? Yep. So just so everyone knows what Arouge is referring to, that's this arrow right here. This arrow is just basically C1 floating in. Instead of using IV, instead of using IV, you actually use C1 as your salt to exclusive OR the next one. Great. All right, not seeing any more questions. So this method is not one-to-one. Great question, Yusuf. That's a really important question. So I'm gonna take a minute just to talk about it. So in yellow, this encryption function, this is one-to-one. E is one-to-one. However, the output of the overall function of the overall cipher is not one-to-one. So while the cipher is not one-to-one, its a building block is one-to-one. Does that make sense, Yusuf? So this, yep, great. Okay. So not seeing any more questions, so we're gonna keep marching on. Clear all my drawings. Back to this mode. So clearly picking a good source of randomness, or rather just a good initial salt is an important thing. So if you're developing a single use system, you don't even need the IV because the encryption, because no one can recover the key. But the whole point of this is to defend against chosen plain text attacks. So you could use a unique IV every time, but you need to sample a new IV each round. But you don't need to send the IV with a ciphertext if you use counter mode. Counter mode is where you, based on the packet number that you're transmitting, you pick an IV based on that. So that's what that means. Really, it's best to use a random IV message and send it with the ciphertext. And just to kind of show you the difference, so obviously I'm going to highlight, I'll annotate these a little bit, but this image in the yellow box, that's the original image. This image in the red box is the image after it was processed by EBC, electronic or ECB, electronic code books. And this is the message that was processed with CBC, chains, or CBC, the kind of chained blocks that we saw earlier. That's the cipher block chaining we just discussed. I hope that motivates you for how much of a difference this makes in security. So now we're going to talk about the data encryption standard, DES. Oh no. Oh, something okay, Jared? Oh, just why is it so bad? Okay, yeah, this is really bad. So DES, sorry, I thought something terrible happened. So DES, it was, it was actually the kind of suite of security developed by IBM that ECB was a part of. But DES was a different standard. It was developed with 128-bit keys and 128-bit blocks in the 1970s. The US National Bureau of Labor Standards requested a different version of it that used 56-bit keys, operating on 64-bit blocks. It was widely criticized and speculated to have been made deliberately weak by certain US intelligence agencies. And just to clarify what I mean by that, I mean the NSA for sure, without a doubt, played a huge role in making that very weak. It's hard to draw with a mouse. Yes, the NSA definitely did something there. There's many fancy ways to break it, but you can actually brute force the 56-bit variant in 1998. In 2007, they were able to brute force it in 12 days. So it's just not that secure because of its short keys. So that brings us to AES, hopefully an acronym some of you recognize. This was developed by 2 Belgian cryptographers. I talked about the US government. It supersedes DES in 2002. First and only publicly accessible cipher approved by the NSA. This is kind of suspicious. You know, if the NSA is saying go ahead and use it, that might mean the NSA can break it. And they've proven to not be a very trustworthy institution over the years. All of that being said, it is like something they use for their own documents. So at least we know it's not secure against other people. And other fun parts about it. Oh, the actual algorithm. Let's get into the algorithm. Let me go ahead and clear all drawings. So the algorithm, first derive round keys using a key scheduler from a cipher key. Now, round keys, this is not a term we discussed before. All a round key is you have an initial key of, you know, you have an initial key of some length, and you want to make it a bigger key. This process, this is the process of creating round keys. So we'll call this a ridge key. We'll call this round key. It's not padding, Jared. That's a great question. It's actually a mathematical process that you use to derive. We can talk more about it at length later, but for the purposes of this lecture, it's not just padding. The round keys are computationally indistinguishable from a random string of the same one or a random key of the same one. So that's kind of what the round key method is doing. And once you have your round key, you expand your current key into the round key, complete your encryption rounds. Each round is a non-linear byte substitution according to a lookup table. So basically what that looks like is you've got a whole bunch of bytes. Let's say these are your bytes. You kind of pick, you pick some of these. Oops. So you pick some of these like this one, or like this one, or maybe this one, and you substitute them according to a lookup table where you have B1 and you have transforms B1, or you have B2 and you have transformed B2 ... So that's what we mean with a nonlinear byte substitution in the lookup table. Then you just shift the rows. The last 3 rows of the message are just kind of cyclically shifted. These messages come in this format of So these just show up in these little formats. And all this is saying is that these last 3 rows are being shifted around. Then you mix up the columns. So you just combine 4 bytes in each column according to a linear mixing operation. That's just mixing the columns around, kind of like swirling them around. Then you exclusive OR that final little matrix with the round key. When you've done that for the required number of rounds, it's usually between 9, 11, and 12 rounds. You have your final encryption round. It's the same nonlinear byte substitution, the same shift rows, and the same exclusive OR, but no mixing of the columns. Are there any questions on this AES algorithm and how it works? Check. No, you will never have to implement this from scratch for an assignment. In general, if someone tells you to implement cryptography from scratch in a production setting, that's a really bad idea. Cryptography's greatest weakness is almost never the math. To break AES, you would need to like do some crazy stuff mathematically, but there are other ways of breaking AES that are not that complex, that are like side channel attacks or things like that. So every time you implement cryptography, you're kind of just saying, I'm going to make a bunch of vulnerabilities. We always use someone else's cryptography and we always have it vetted by a third party. So no, I will not have you implement this from scratch. I may have you implement parts of it for a programming assignment, but I'm not going to. Yeah, exactly. If you make your own crypto, you are not making a good decision. It's yeah, you always want to use other people's implementations that have been widely tested and analyzed. And a great way to make sure no one ever uses your cryptography algorithm is to patent it. There was actually a really good stream cipher from 2008 that no one can use because it was patented. And it also, there was never an open source implementation of it. So no one ever could audit that it was done correctly. And no one can make another version of it. So even though it was mathematically a better stream cipher, because it was more efficient, no one could ever use it. Okay. That brings us to the end of lecture today. A couple of people in their assignment indicated that they liked the 1.5 hour length for lectures, with an extra 30 minutes for maybe questions.